My name is Hazel Murray, and I'm going to present myself and David Malone's paper called Choosing Word Lists for Password Guessing and Adaptive Multi-Armed Bandit Approach. So the contents of our talk is going to start with what our motivation was and the goals of the research. And then I'll introduce what the multi-armed bandit problem is, how it applies to password guessing, and then I'll kind of discuss how we use maximum likelihood estimation to estimate distributions of password sets and to inform our guess choices, and then I'll discuss the results and the impact. So to begin, firstly, password guessing, the way it usually works is there's like hashed and salted passwords that are stored, and we basically guess a word, hash and salt it, and see if it matches, the stored value. So basically, an attacker will just keep guessing words until they get a match, and then they have a success. So when we're talking about password guessing, or at least users' password choice, we know that users from the same using the same language will use similar passwords. And we also know, or we think, that users from the same nationality will likely use similar passwords as well. And the other thing we know is that users that are using the same websites, there will also be similar passwords between those users. So for example, people using LinkedIn would be more inclined to use LinkedIn as a password, or something like job search that relates to the site they're choosing. So when a password guesser wants to guess a set of passwords, they basically will usually make a few guesses and then have a look at what successes they got. And that will tell them, what language they're looking at. Sometimes they can look at the usernames to figure that out and things like that. They might know what site the passwords come from, they might not, but they'll be able to basically learn features of the password set before then tailoring their guessing and making loads more guesses. So our question is whether we can automate this investigation process. So in particular, can we learn things about the nationality of the users, or can we learn things about the site that the passwords were leaked from, just by doing password guessing? So what we're going to look at in order to try and solve this is a multi-armed bandit. So each one of these machines in the picture, these gambling machines, is called a bandit, and the multi-armed just means that there's multiple of them that we can play with. And each machine provides a random reward from a probability distribution that's specific to that machine. And a gambler that's going to be using all these bandits is faced with the crucial problem of how much time to spend exploring different machines and how much time to spend exploiting the machine that seems to be giving the best rewards. So the objective of the gambler is, over a series of 12 hours, to maximize the sum of all the rewards they get. And they can do this by learning about the probability distributions of the certain machines and leveraging that. So essentially, it's an optimization problem. And it's one that we have kind of some mathematical techniques for solving. And it's also one that I think applies to password guessing. So I'll explain that next. So our idea is that a password attacker has lots of different dictionaries they can choose from. So they might have multiple language dictionaries, they might have lists of common passwords, and they probably have leaks from loads of different sources, prior leaks, that they have hacked or were in plain text. And they might even know things like personal information about the individual users or things like that. But essentially, there's this huge corpus of information, which we call dictionaries or word lists. And they want to guess a password set. And the crucial problem they're faced with is what order to use the dictionaries in, and what dictionaries to use in order to maximize the returns on guessing this password set. So I'm going to explain in the next slide how we can basically, use the tools of the multi-armed bandit in order to link to password sets. But this is essentially the idea that we have a set of dictionaries or a set of word lists, and we want to choose them in a smart way in order to inform what order we make the guesses in. And the order we make the guesses in is really quite important, because if you take, for example, online guessing, if I'm guessing online, maybe there's a lockout after like 10 wrong attempts. So making like good guesses straight away and in the right order is really important for like maximizing returns on guessing. Okay. So again, imagine we have all these dictionaries and we have the password set, which is what we're trying to crack. So we begin by making a guess from one of the dictionaries, and this can be an informed guess based on like, the most probable, like the most common password across all dictionaries, or just something that seems like a logical guess. So we've chosen 1, 2, 3, 4, 5, 6 because that is the most popular used password. And we guess the password set. So we hash 1, 2, 3, 4, 5, 6 and compare it to each of the users, hash values, the encrypted things here, and we see how many successes we get. And let's say of the 200 users' passwords, 8 users chose 1, 2, 3, 4, 5, 6. So that means then I look back at my dictionaries and I see, okay, well, how often did 1, 2, 3, 4, 5, 6 occur in my dictionaries? And I see in the first dictionary, it occurred 1 out of the 90 users in that word list had 1, 2, 3, 4, 5, 6. In the second one, 8 out of 200, an exact match, which isn't as likely in actual, but like, let's say it's an exact match. And then the other one is 40 out of 150. So looking at this, we say that the distribution of the password set based on this one guess is highly linked to that second dictionary. So we've started by guessing 1, 2, 3, 4, 5, 6. And the idea is then we say, okay, well, it's highly likely that it's from this second password set. So maybe I'll choose my next guess from that password set. And we basically keep making guesses. And each time we look at the distributions of how many successes we got with that password. And then we compare back to all our dictionaries to see which dictionary has the similar distribution. So essentially, there's 2 learning techniques here. The first one is matching the proportions seen in the password set to the proportions seen in the dictionaries. And then the second thing we need to do is, based on that information, we need to make an informed guess. So I'll talk about the first one first. So that's the matching proportions. So it's not quite as simple as going, 8 out of 200 had it in the password set, 8 out of 200 had it in the dictionary. Oh, that's a perfect match. We need to deal with like all the different information we get after, n guesses. We need to be able to collate all that information. And the way we do that is we use this maximum likelihood estimate. So it's maximum likelihood estimation is a method of estimating the parameters of a probability distribution using observed data. So our observed data will be all our prior guesses where we saw what the result was, like what the reward was, which is the number of successes. So based on all that prior data, maximum likelihood estimation tries to estimate parameters. And in our case, parameters are basically weightings that were assigned to the different dictionaries. So this is our likelihood function here. And we essentially are trying to choose different Q values to give us the maximum likelihood function value. So it's kind of like an iterative approach. If we try like a certain set of Q values, and we then try another set of Q values, and we're like, oh, that gave us a higher maximum likelihood, like as in the likelihood of this new set of Q values is higher. And then we kind of iteratively figure that out. And the way we're iteratively figuring that out is using gradient descent. So yeah, the likelihood can't usually be like explicitly calculated. It's kind of, yeah, it requires something like gradient descent in order to converge towards the Q values that best describe the set. And one of the nice things about our setup for our likelihood value, which describes password guessing, we were able to prove that the maximum likelihood function is concave, which means that there's only one maximum. So our gradient descent should always converge to it, which is good. Okay, so that's kind of like how we're, estimating the weightings of the dictionaries. We're using maximum likelihood estimation and gradient descent to estimate the weightings. And then the next thing is, once we have those weightings, how do we choose the dictionary? So, I've assigned like different weightings to each one of the dictionaries I have. And we kind of say that there's 3 ways you could choose your guesses based on these weightings. You could completely ignore the weightings and just continue to randomly choose a dictionary to guess from. And this is what we call like exploring. So we continue to try all the different dictionaries, even though we've got some information about what one might be best. So our next guess will just explore from it will just take a guess from a random dictionary. So that might be good if we just kind of keep wanting to learn things, but maybe we care really more about successes usually. So we probably don't think the random one will do great at guessing. And the second way is that we choose the next best password from the dictionary that seems to be the best match. So we just say, okay, well, whatever dictionary was weighted as being like the highest weighting, whatever one has the highest weighting, we're just going to use that for our next guess. And this is called the exploiting method. So the problem with this method is that you're probably going to keep choosing, you're only learning about the dictionary you're guessing from, kind of. Well, you are learning about all of them, but you're exploiting the dictionary that's currently the best. Yeah, so that's how we're going to choose our next guess. We see this one has the highest weighting, so we're going to guess from this one next. And then the last method, and this is kind of a method that we're particularly interested in, is we could choose our guesses based on information about the frequency of the words in the dictionary and the weightings of all the dictionaries we have. And we've called our method, this method, Q method. And I'm going to explain this method in a bit more detail. So let's say we have 2 dictionaries with the following words in them. And usually what we do is we just guess the highest frequency words first. Whatever ones appear the most, guess those, because they're going to probably give us the best results. But here we'll also take into account the weightings of the dictionaries. So let's say I've just got 2 dictionaries and it estimated the first dictionary as having a weighting of 0.3, and it says the second dictionary has a weighting of 0.7. And what I do in order to figure out what word I should guess next is in dictionary 1, the word by appears 3 times. So I have out of 8 total words. So I've got, this is 3 out of 8 is by, and then I multiply that by the weighting of my dictionaries, the Q1. The word by appears once in dictionary 2. So that's 1 out of the 8 words. And that dictionary has a weighting 0.7. And that basically gives me this Q value, or this Q score for the word by. And that's 0.2. And then I can do the exact same thing for all the other words. But let's say I do hello. And hello only occurs once in dictionary 1. So it's 1 out of 8 multiplied by 0.3. And in the second dictionary, it occurs twice. So it's 2 out of 8 and it's multiplied by 0.7. And importantly, notice that if we were just looking overall, by appears 4 times and hello only appears 3 times. But according to the weightings of our dictionaries and what dictionaries we weight as more important, we would actually, in this case, end up guessing hello next. So the idea is that not only are we combining information from all the dictionaries, we're using the weightings to inform what guess to choose as well. Okay, so that's kind of like how we set up the multi-arm bandit. So I'm now going to talk about the results. So we began by running simulations. So one of our simulations is that we created a fake test password set. So we basically had 4 word lists, and these were word lists of like leaked passwords from, I think Hotmail had a leak of about 10,000 passwords or users' passwords. Computer Bits, I think 2,000 passwords were leaked there. Flirt Life, 98,000 passwords were leaked in that Flirt Life leak. And Webhost was a few million passwords, not sure exactly how many, but like a big password set. And what we did is from each of them, we just took a random sample. So we took 1,000 from Webhost, we took 3,000 from Flirt Life, we took 5,500 from Hotmail, and we took 500 from CompuBits. And this made up, we took all of those, randomly sampled from those 4 dictionaries, and we made up a new password set. And that new password set has a total of 10,000 passwords. So then what we did is we decided we would guess this new password set using all these dictionaries. And if our multi-arm bandit and gradient descent method is working correctly, it should be able to weight the different dictionaries according to the weightings we know they have. So we know that, for example, Hotmail accounts for like 55% of the total new password set. So it should have a weighting of 0.55. So on the next slide, I've plotted what it's estimating these weightings as. So the black lines are the true weightings, and then the plotted values are the estimates for the multi-arm bandit. So essentially, the x-axis is telling you the number of guesses we've made. So let's say after 1 guess, we say, okay, you've got 1 guess of information. How would you weight the 4 dictionaries? And then after 10 guesses, each guess we plot again. We get plot again after each guess, but yeah, we ask it again. Okay, now what do you think the weightings are for the 4 dictionaries? And we can see it does a pretty good job. Like I would say after 3 guesses, it's got a pretty good idea of where things are, but definitely by 10 guesses, it's absolutely worked out where the different dictionaries should be. So we've got, this is Hotmail, and it's about 0.55. This is Flirt Life, and it's weighting it as 0.3, which is where it needs to be. Struggles a bit with Webhost here, dropping a bit below the line, but again, it has some idea that it's kind of down here at 0.1, and the same for Computer Bits, that's 0.05, and it has it pretty well down there as well. So yeah, this basically tells us that given firstly, the important thing is that these are just small random samples from the entire dictionaries. So if we had taken the dictionaries, exactly the entire dictionary and used that to make the word list, then this would be, near perfect lines. But, we wanted to have some kind of randomness in it and ambiguity. But we can definitely see that our multi-arm bandit method was able to estimate the different weightings with pretty good success. And we did this for lots of different simulations. I'm just showing one here. But yeah, by 10 guesses, it has a pretty good idea of what the most important and least important dictionaries are. So once it was able to estimate the weightings, we then want to use weightings to inform guesses. So what I'm showing here is the 3 different methods we mentioned before. The Q method, the just picking from the best weighted dictionary, and then just randomly choosing a dictionary to guess from. And then the black line is the optimal method. So that basically says, if I guessed the passwords for this password set in the exact right order, how many users would I have compromised after 20 guesses, after 40 guesses, and so on. So yeah, our Q method does the best. The best method is next, and then the random method. And it's not that far off the optimal guessing strategy that we'd expect. So this was for the simulated password set. So the next thing we did look at is we just took like a non-simulated password set. We just took the list of all the RockU passwords, and the RockU passwords are pretty highly studied, so it's kind of nice. That means we have some comparisons, but essentially what we did here is we tried guessing with just individual dictionaries, like the Flirt Life dictionary, the Web Host dictionary, like the Hotmail and the Computer Bits dictionary. And then we tried the multi-arm bandit method of combining the guesses from all the dictionaries. And we can see that using the multi-arm bandit, we got much better results. Okay, so the next thing we were interested in is the nationality of the users. So we saw already that if we know that the user's passwords come from a specific site, then we can pretty well estimate, you know, what site the user's passwords came from. So now we want to know whether we can estimate the nationality of the users, or like predict that. So the important thing here is that, yes, we know people from different nationalities choose different passwords, or at least we suspect they do. We're pretty sure they do. But it would be very easy to tell the difference, or like for like an automated program, to tell the difference between a Chinese user's password and an English user's password. Because I mean, that's very obvious. It's, you know, there's not much of a challenge in that. So what we decided to look at is we looked at English users' passwords, and we looked at German users' passwords. They use the same, you know, alphabet, and they're both European, Indo-European languages. And then what we also did is we looked at an even more difficult challenge. We looked at English users' passwords and Irish users' passwords. So in this case, not only are they using the same alphabet, they're using the same language. Most Irish people speak English as their first language. So we're basically comparing whether there's like cultural differences that mean that the passwords are different, rather than just language differences. And we're trying to see whether the multi-arm bandit can, you know, discover these. So I'm just going to show the results for the Irish users, but the German users are also in the paper. So what did we do here? We basically made so the computerbits.ie that I mentioned earlier were 2,000 passwords that were leaked, and it was for an Irish website. So all the users, we can assume, were Irish. So what we did is we wanted a dictionary of Irish users in order to be able to, you know, guess using Irish passwords. And to come up with this dictionary, we took something called collection number 1, which is like a huge password corpus. And we chose like some subset of that corpus, because it's really huge. And we took all the users who had email addresses ending in .ie, the top level domain for Ireland. And we extracted all those users' passwords, and we called that our dictionary of Irish users. So that's this green line here. And then we put in the hotmail.com users. So Hotmail, it's a .com website, so it is pretty international. And there's Flirt Life users who are Turkish and German users. And we can see that by 10 guesses, it definitely says that when we're guessing computerbits.com, even though there's no actual overlap in the, you know, users between the two, the Irish users dictionary and the computerbits.com password set, it immediately sees that the Irish users' passwords are the best match. So it gives them a 0.9 weighting. So then what we do is we see whether this also will improve guessing. And what I've plotted here is the multi-arm bandit, which is the yellow line. If we just guessed using all those Irish users, it's the purple line. And I mentioned that we took all the Irish users with the .ie email addresses out to make the Irish users dictionary. So the old users is that entire password, that entire data set of passwords, but like, yeah, not extracting the Irish users. They're still in there, but it's the entire password set. And we'd be using that to guess. So yeah, we can see that guessing using like just the Irish users or allowing the multi-armed bandit to learn what dictionary to use is the most effective. Okay, so some impacts of this research. The first thing is use cases for like how this actually is maybe like worryingly applicable to attackers is in an online guesser could guessing a selection of users' passwords from a website will learn from each success and use it to inform the next guess made. So that's kind of like the first use case, is it can be used in an online environment because we can get like, information in less than 10 guesses. And the second use case is if an attacker could gather information by applying the multi-armed bandit to like an offline leaked data set of users from a given organization. So let's say we have the Hotmail leak. I have access to the Hotmail leak, so I could use the multi-armed bandit to learn about Hotmail, choose the optimum choice of word list, and then I could apply that optimum choice of word list to the Hotmail users that are actually actively, using Hotmail at the moment. So I basically can learn from an offline corpus, and then I can apply that learning to, real users in real time. And then the last one is similar. It's the idea that you could select a selection of users' accounts, like online, and you could basically learn characteristics about those accounts until they become locked. And the multi-armed bandit will basically, highlight the appropriate word list to use. And you could then, you've learned based on accounts that you've, locked, because there was like a lockout policy after a certain number of wrong guesses, but you can basically take what you've learned and then use it against the other users at the same website. And you could potentially use it against like the more valuable users or something like that. So it does show that learning characteristics can be automated, and it also provides evidence for the importance of guiding users away from passwords which reflect like nationality or website, because it is clearly identifiable. And also it demonstrates that passwords are measurably different depending on their source use. And it kind of indicates that websites should consider block listing passwords in a way that's tailored to their specific subject matter and users. And in future work, we hope to be able to use it to identify password policies, like what ones are enforced or were enforced at a certain time, to automate the identification of that. And we think it can be extended so that it doesn't even need to work on exact probabilities for the words in the word lists. And that would mean that we could read in word lists that don't necessarily have probabilities attached, say something like users' personal information could be read in or something like that. And that could be seeded throughout the guesses. And the last thing is that we'd like to increase the number of word lists. So at the moment, we kind of did 4 word lists, guessing 1 dictionary, 4 dictionaries to guess 1 password set. So we'd probably like to increase the number of dictionaries and go to failure, just so see how many dictionaries we can try learning from until the system kind of doesn't work anymore. So I'm happy to take any questions you have. I hope you enjoyed the talk.